because I have been a big proponent of coding right from my days here. My master's was in radar and microwave electronics, but I took up computational electromagnetics after that for my PhD. And after that, I completely ditched that domain and went into cloud computing and all that, where I did distributed computing and all that in Huawei. From there, then I moved to industrial IoT and other domains. So basically, I have been hopping several domains. It might look erratic at first, but eventually it all falls back into a plan. Okay, so my interest area is basically distributed AI. Okay, and I have been working on the various constituents that would go into deploying a distributed AI system for past decade or so. Okay, so when I joined Huawei, I was working on you might have heard of blockchain, right? So under blockchain technology, there is a distributed ledger technology, distributed consensus technology. What it means is when you have multiple people, node, machines, whatever, if they can talk to each other, they can share information with each other, okay, and they can come to a consensus about the information of what they are observing from their environment. Okay, bear with me for some time. I'll let you know how this all comes together for electromagnetics. Okay, so specifically the technology is called multi-agent systems. Okay, nowadays you would have heard of multi-agent systems, but it's in a different large language models context. It's a very recent thing. Okay, what I'm talking about has been like there for 3 decades. Okay, multi-agent systems where you have agents, software agents. Each agent is smart enough to understand its environment, but the problem is each agent would have a limited view of the environment. Let me give you an example. A radar platform, for example, an aircraft carrying a radar. Okay, it would have a limited field of view in a particular time. Okay, it would be able to only scan at certain angles. Okay, and it might be a mobile platform. It's an aircraft carrying a radar, so it's a mobile platform. Now you could have multiple such radars deployed in an enemy territory, and you are trying to assess the situation in the enemy territory. Okay, now each radar might be able to track one target as long as the target is in its field of view. Right, the moment that target moves out of its field of view to another radar's thing, field of view, right, is there a mechanism where the two radars can, you have the baton race, you know, right, when players run, right, so you have to pass on the baton the next one. So you have to track this target when it moves out of one field of view and goes into the other one, right? For that, what all technologies are needed? First of all, sensor fusion. Here, multi-platform sensor fusion. Also, it could be multi-target sensor fusion. So there could be multiple targets that one radar is trying to detect and track, and that it has to pass on that information to the other radar, right? So for that, you need a communications infrastructure. Okay. So in what I started talking about multi-agent system, each of these radars are agents, so to speak. They are intelligent enough because they might have some machine learning algorithms to interrogate the environment and understand what's happening in their environment. But since they have a limited field of view, they can talk to each other to come at a consensus about what's happening in the environment as a whole. So this is where artificial intelligence is headed going forward. This is called distributed AI, distributed artificial intelligence. So that is one pillar of what I am working on right now. The second pillar is distributed edge computing. Okay, what distributed edge computing does is it makes it happen, right? So whatever one radar is trying to do, you need to do the signal processing on the radar itself, right? You don't have enough bandwidth or enough communication link bandwidth to send it to a ground station, process it, and so that would all become a centralized processing platform. Okay, if every radar is talking to a ground station and ground station is the mastermind, what if the enemy shoots down the ground station itself? Everything is useless there, right? So distributed edge computing is when all this processing, the DSP and the machine learning is happening on the radars itself. Okay, the third thing that can make this happen, that enables this, is called mesh communication. So what I'm trying to show today is mesh communication. Okay, wherein all these radars no longer need to talk to the ground station. They can share their information among themselves. Now, during our lunch break, we were discussing about drone swarms. Okay, that's a big thing these days, right? So what I was telling to my friends here, drone swarms are no big deal actually. When you fly thousands of drones, you have seen light shows and everything, right? These drones are actually not aware of each other. They are all being controlled by the ground station. And whatever light shows that you see, light patterns and everything, that is all pre-programmed from the ground station and uploaded. Okay, the drones are actually not moving. They should not move, otherwise they will collide among themselves, right? What I am trying to show you today is something that would enable the drones to talk to each other. Then there is no need for them to link up with the ground station. They are aware of each other's presence, and if they have GPS, they would be pretty much in close proximity to each other. They would not collide. Now, what's the use further than this drone swarm lighting shows and all in defense forces? For example, drone swarms for, you are seeing Ukraine, what's happening, right? So there is one application of you upload a mission objective to the swarm. The swarm goes into the enemy territory, and with no communication link back to the ground station, the swarm would go and try to achieve its mission. And some of the drones get shot down, let's say. The other drone should on the spot be able to, on the fly, should be able to take up the responsibility of their fallen comrades and should be able to execute the mission. This is the highest level of drone warfare that will happen in the next 5 years time. Okay, and these are the technologies that will make it happen. Okay, so the objective of today's talk is, of course, the backdrop is mesh communication. What makes that happen is SDRs, software defined radios. Okay, so what's a software defined radio? Let me first show you the agenda of the talk. We'll start with what is an SDR, how does it look like, and there is something called complex baseband that I'll come to. Okay, then I have some SDRs with me. It's ADLM Pluto. ADLM means analog devices active learning module. So it's a very cheap SDR you can buy yourself, Pluto SDR, and it's good to experiment with to begin with. Okay, and then I'll talk about Pluto's HDL design. HDL means hardware descriptor language, basically FPGA. So whatever you build onto an FPGA is called HDL design. So once you have built that design, how do you interact with it? Right, you need a firmware stack on top of it. So I will talk about that also. Then in embedded systems, you have hardware and there is some firmware running on top of it, mostly written in C and all that, and you compile an assembly and it runs, right? There is another thing which is an operating system, which makes several things happen. Not only the compute on this device itself, you also need networking. Networking is usually, it's implemented by a TCP/IP stack, right? So all these layers are taken care of the operating system kernel stack. Okay, so I'll talk about that also. Then how to build your software that can run on the SDR. Then I will give an example of how you can build your own OFDM modem. All of these almost free, like from open source tools. All you need to buy is just this Pluto thing. Okay, and then I'll finally give a demo of this. So let's start with the very basics. Okay, so this diagram is probably you would have seen all the time, right? This is a typical super heterodyne receiver. Transmit is also almost similar in the reverse direction, but let's start with this. So there's an antenna. There is a pre-processing that is required in the form of a gain, okay, because the signals are very weak. You go down through the first mixer stage. Okay, so whatever RF is coming here, you mix it with this LO is also of the same RF. So this signal comes down to the IF. Okay, that IF is basically a bandpass signal that you have to pass it through a bandpass filter, of course, and this last mixer stage then finally brings it back to 0 IF. Okay, and that 0 IF is what you send it to your analog detector. It could be AM. For that you need to use a diode rectifier, or if it is FM, you use phase lock loop. Very basic, right? What's the problem with this? Of course, I have written there, you can read it off, but what's the problem with this? Most of the components are analog in nature. In fact, the entire system is analog in nature, which degrades with time and temperature. Okay, so if it degrades, you have to go in the field and retune it or change the parts and like that, right? Does software degrade? Once you have written a software, it will not degrade in hundreds of years also, right? So the thing is, this is one end of the spectrum where you have everything analog. The other is this, where everything is in software, right? So you connect the antenna directly to the ADC. Of course, there is a gain also and all, but you directly connect to the ADC. What's the problem with this architecture? Can you think? Now you have to sample an RF signal, right? Your RF, if you're talking about communication systems like sub 6 gigahertz and all, what are your options available for such ADCs? I've written here. So if you are going with Xilinx RF SoCs, they have on board ADCs, which I have given an example of 16 channel, 14 bit, 2.5 GSPS. The price of each chip is $36,000, right? Close to 36 lakh rupees just for the chip. And then you have to get that chip, build a board around it. Just imagine the cost. So this is not something which is meant for people like you and I. It is meant for defense forces and all, where such projects come across. Okay. You might say, okay, why do I need a SoC? If I just need the ADC, why do I need all the processor and everything around it? You can. There are ADCs available like that, but they are also costly. 1.1K just for if you're buying in sufficient numbers. The problem with that is you have to interface that ADC with a FPGA, so you need a IP core called JESD interface, okay, which is very difficult to understand and program. So these are the challenges. So is there a middle ground? Yes. So this is what everybody uses these days. Even Pluto has this kind of an architecture. Okay, what does it do? So you have an antenna and a gain, and then you have a mixer. There is nothing beyond that, just the ADC. So this mixer is responsible to bring the RF directly to zero. It's called direct conversion receiver. Okay. Now there is a challenge with this architecture also. We're referring to that architecture. So let's say this is your RF signal. This is your LO. Okay. You mix them, you get sum and difference frequencies. Okay, the higher frequency you can take it out by using a low pass filter. This is what you end up with. Okay, this output signal just before the ADC stage has an amplitude. Let's say this was an amplitude modulated signal that was coming in. So you have amplitude and you have a phase shift. Okay, so what's the problem with this signal? Basic trigonometry. You are interested in extracting information out of A, because this is what is going to be detected by the diode rectifier, right? The amplitude variations. But there is one guy sitting here which is going to spoil your game. It is this guy. What happens when phi is 0? Cos 0 is 1. And what happens when phi is pi by 2? 0, right? So that guy is going to kill this A. This A is present. It's not going anywhere. But this cos phi, depending on what's the value of phi, is going to kill that signal before even it reaches the diode rectifier detector, right? Why is that happening? Why is this phi changing? What is phi here? If you see this signal, this is incoming signal, RF signal. So it has an amplitude variation. It has a frequency term in it. What is this phi? Phase shift or delay, right? So if you are holding a mobile phone and there is some tower, there is a fixed distance between you, right? There is a fixed phase shift between you. If you move, that phase shift is going to vary. What this means is, if you move with your receiver, you are going to see periodic nulls and maxes. So this signal is going to feel phase cancelling out, okay, as you move. That's not something desirable. Okay, so what can we do? So clever but simple. This is what your line of thought should be. What do? Okay, this guy has a problem that it goes to 0 and 1 periodically. But I can have another signal which also goes to 0 and 1 periodically, but not at the same time as this guy goes, right? So when this guy dies, the other one pops up. When that guy dies, this one pops up. This guy. sorry, if you take the LO, another LO signal, so this one was cos omega LOT, this is sin omega LOT. If you mix this signal with the incoming signal, you get this term, right? So what if I add these two? So when this goes down, this goes high. When this goes down, this goes high. Okay, understood? So that's called quadrature signaling. Okay, so how do I implement it? This is how I implement it. So you give your LO directly to one mixer, and the other one you phase shift, it becomes cos becomes sine, and you give to the other mixer. Give those to the 2-channel ADC, and what comes out is 2 real signals only. There is nothing complex about it yet, right? I have put them here after ADC, means these are digitized signals, but there would be analog counterparts here also. So here would be analog counterparts, there would be digital counterparts, but these are mind you, real signals. It's only when you store them in a computer, you would want to store them as A cos phi plus J A sin phi, right? So suddenly now, instead of receiving a real signal and storing them as 2 real signals, you are taking a real signal and storing them as a complex signal. Okay, so this signal is a perfect representation of this signal, but only in complex domain. Okay, this is called complex baseband. Why baseband? Because you took something in RF band and brought it down to 0 hertz carrier. Okay, so this is your baseband signal, and the beauty of this is you can bring in your complex arithmetic directly. So how can I extract A? This way. How do I get phi, the phase shift? Like this. Okay, then there are some modalities of, like, if your input signal is a real signal. Okay, just a trivia, you have done DSP, right? Signal processing. So what's the spectrum of a real signal? How does it look like? When you take an FFT of a real signal, how would it look like? Oh, I have written there already, you can read it out. It would be conjugate symmetric. Okay, what this means is, you take a real signal, you know, right? Sine, cos, or a combination thereof. A real signal, you take and take its FFT. You can plot the spectrum from Fs by 2 to minus Fs by 2, right? There is 0 in the middle. The signal, the spectrum part, which is between 0 and Fs by 2, will have a mirror image in the other side. Okay, but it would be conjugate, it would be ulta. Okay, but the beauty about complex, so what I'm trying to get at is, for real signals, the spectrum is only half, 0 to Fs by 2, because the other one is trivially related to the first one, which is a mirror image. But if you take a complex signal, incoming signal itself is complex, its FFT will be occupying the entire bandwidth, Fs by 2 to minus Fs by 2. Okay, so what I'm trying to say is, by using complex baseband, you can cover much larger bandwidth compared to a super heterodyne or IF receiver, those kind of things. Are these things understandable? Yeah, okay. Because I understand you guys are coming from a microwave and radar and those background, right? But what I'm trying to get at is, you should start thinking of technologies which are like bridges between microwave domain and digital domain. That's the best way to learn either of these technologies. If you just learn digital systems, embedded systems, you will get job in that area, but it's of no use, right? There are plenty of people doing that already. If you take microwave domain as your career path and everything, but you don't know how to code around it, it's of no use again. Right? Real things get built when you bring together multiple disciplines, or at least you have some overall overarching knowledge of these disciplines. So what I'm trying to get at today is, SDR is one approach where you can bring in both radio frequency stuff and digital stuff together. Okay, now it will be over soon, don't worry, but these are key things that I wanted to talk about. So you might know of Shannon's information theorem, right? Do you know that? Anybody? You remember that formula? Channel capacity is equal to bandwidth times log of 1 plus SNR, right? That's Shannon's channel capacity theorem, basically. So essentially, what Shannon theorem says is that you cannot create information artificially. Okay, whatever information is there in a signal will be captured by its bandwidth. That is why you have the capacity related to the bandwidth. Capacity is related to the proportional to the bandwidth, right? So let's say my original signal was spread out in this entire bandwidth. Okay, now that signal, among that signal, the signal which happened to be in this domain was my signal which I am interested in. Rest of the other signal probably was a spurious signal or somebody else's signal. I'm not interested. When you're talking on a phone, you are covering a much wider band. Your portion of the band is very limited. Rest is occupied by other users, right? You're not interested in all that. If you're not interested in somebody else's band, that is not considered information for you, right? So your information is only in this band. So why should I take an endpoint FFT on this entire band, right? Because my information is here. So effectively speaking, if my information is here, my bandwidth of interest is also here according to Shannon. Why should I sample all this way, right? So basically from my perspective, this is waste of bandwidth. So what can I do? If I start reducing the bandwidth, am I losing information? I'm probably losing signals, but they belong to somebody else. My signal is still there, right? I'm centered here, right? So you have an opportunity to reduce bandwidth, reduce your signaling rate. Okay, that is what it means. So how do you do that? It's not very easy because there will be some signals here. If you try to reduce how do you reduce the sampling rate of a signal? So you have a signal with certain sampling rate, discrete signals, right? How do you reduce the sampling rate? You start throwing out parts of it, right? Let's say every fourth component you are throwing off, you are keeping, and rest three you are throwing off. Okay, so that way you are effectively saying what is sampling? Basically you close your eyes, open your eyes, close your eyes, open your eyes, whatever signal in front of you, you're taking snapshots of it. So the rate at which you are closing, opening your eyes is the sampling, basically sampling rate, right? So if I choose to, I already have a sampled signal in front of me. Now I'm asking you to close and open your eyes at a slower rate. You would still be sampling the already discretized signal, but you would be throwing away a lot of the content from that, isn't it? So that is what it means. So reducing this bandwidth means reducing sampling rate, which is what I have written, Fs by 2d. Okay, the d is your decimation factor. Decimation means throwing away samples. Okay, so every fourth sample you are keeping, and rest all you are throwing. For example, decimation by 4. That would be an example. The trouble with that is aliasing. Are you aware of aliasing? It's a big problem for ADCs, right? So if I give you a wideband signal and I give you an ADC and I ask you to sample it, what's the problem? Can you directly sample it? So every ADC has a maximum sample rate, right? And if you try to give it a signal which is higher than the maximum sample rate, what's going to happen? ADC will sample it anyways. What are you going to get at the output of that? Mirror image. It is an aliased image. So how do I say? You have a slow varying sinusoid signal which you are observing with your eyes by the shutter mechanism, right? And I'm asking you, you should not change your shutter mechanism speed, the rate shutter speed. Okay, you are still observing that signal. So when you draw it on the paper, you see samples of that thing, right? Now I'm asking you, maintain that shutter speed. Now I'm going to increase the frequency. What's going to happen? At some point of time, the signal would have become so fast, but you are still opening and closing up. From your perspective, it is some low frequency signal only, right? You are still trying to note it down as a low frequency signal. This is what is called spectrum folding back. Okay, so higher signals beyond Fs by 2, which is Nyquist first Nyquist zone, will keep folding back into the first Nyquist zone itself. This is the working principle of any ADC. Okay, So what I'm trying to say is you would have these signals, but these are beyond this domain where you are interested in. If you don't take care of these, ultimately whatever domain you end up with, they will have a mirror image there. Okay, so first you need to get rid of them. So this is the principle behind FIR decimation. Okay, so first you have to put a FIR filter so that these guys go away. Of course, this filter I have shown, I have exaggerated here, doesn't completely go down to 0, maybe 80 dB or something. You would still have some parts left which will show up in your domain, but they will be much lower than your desired signal. Okay, first FIR, then decimate. That's the proper way of doing it. Right. Why did I say all these things? Okay. So so this is what the internal architecture of a Pluto SDR is. Pluto, by the way, I've been talking Pluto. So this is that SDR. Okay. Now I hope things will make sense, because now this is the receive path, this is the transmit path. This entire IC that you see, this is called the transceiver IC. Okay. For any SDR, there would be an RF front end. Okay, then there would be a digitizer ADC, and from there the data goes to an FPGA or a PC where you do all your rest of the DSP. Okay, this chip is just probably one portion of the chip. I think I have the picture on the first page itself. This is the opened up view of that. So here is the FPGA, there is the chip. Okay, transceiver chip. Right. Now look at the receive path, because transmit path is just the same in the opposite direction. Okay. Do you see any resemblance to whatever I showed so far? So your input signal comes in, goes to two mixer stages, one with cos, the other with sine, because there is a phase splitter here which will induce the phase shift. These two paths now go to two ADCs, or you could have one ADC with two channels. What on earth are these things? So this is what is called a half band filter. Okay, what this does is whatever sample rate the input signal is coming in, just reduce it by half. Reduce the sample rate by half. Okay, so the decimation thing that I showed you here, this is what it is doing, except it also has inbuilt FIR filter in it, low pass filter, sorry. Okay, so a half band filter, if you see its implementation in books or anywhere, you will see that there is a filter in front of it, and then it will start throwing every other sample. Half rate means every other samples you are retaining and rest of the samples you are throwing. Okay, why am I doing that now? Why am I trying to reduce the sample rate? Now go back a little. Is this visible here, this number? No, right? Okay. So there was an antenna here, there was some low pass filter and everything, whatever you wanted to keep in the RF domain. That signal came in, you are restricting that bandwidth in this region, which is 200 kilohertz to 56 megahertz. That's your RF bandwidth, right? RF or IF bandwidth, as you might call it. Okay, so whatever signal that is coming in, let's say LTE signal, 5G signal, whatever is coming in, that's a whole lot of signal, but you don't want the whole lot of signal to pass through your system, right? You want to focus only on certain bandwidth, RF bandwidth. So 56 megahertz is your RF or IF bandwidth that comes in here. Now, what do you think should be my Nyquist frequency to sample this high signal? What should be my minimum sample rate to avoid aliasing to sample 56 megahertz signal? 112 megahertz, right? Then why are they using 640 MSPS here? Million samples per second, or megahertz as you might call it. So you are fine. Nyquist theorem says that if you sample this incoming 56 megahertz at 112 megahertz, you are fine. You can easily reconstruct the signal, but they are oversampling it. And on top of that, you are oversampling, and then you are throwing away the samples. You are reducing the sample rate in the further down stages. Now, why is that? So there is one reason to do that is that there is something called sigma delta ADCs. You might have heard of them, right? They have some function called noise shaping. So when you oversample it, right, you are spreading out the noise in a larger band. And fortunately, when you do that, when your band of interest is only a proportion or a small portion of this entire band, you have now spread out the noise way further, right? So now you cut down the rest of the band, and whatever you are interested in has a very low amount of noise. So that is one of the reasons. Okay. The other thing is a little technical. I don't think I'll be able to cover here, because this data rate is fixed. No matter what sampling rate you choose here, this sampling rate has to be chosen so that this sampling rate has to be chosen along with these filter coefficients so that it ultimately ends up at 61.44 MSPS. This is the standard signaling rate which is expected out of any transceiver chip in any modem systems that you build. Okay. So this 61.44 MSPS means there are how many channels here? One I channel, one Q channel, and this chip also has two receive paths, RX1 and RX2. So total of 4. Okay. So each channel is something like 15 MSPS. Okay. I think I have written here also 15.36 MSPS per RX path. Okay. So till here we have received an analog signal, digitized it, brought it to a standard sample rate, and now this thing can be consumed. Consumed how? Now how do I send this data to my DSP algorithms? Where are my DSP algorithms running? Okay. So traditionally, or this is how it is done, basically you connect your transceiver chip to an FPGA. Okay. Now, have you guys ever worked on FPGAs? Anybody here? Not yet. Okay. So basically what an FPGA is, whatever digital logic that you want to design by logic gates and everything, you can do it in an FPGA. Okay. Now whatever, for example, there are tools where you can take a C program and convert it into HDL and deploy it on an FPGA. So FPGA is an implementation of hardware parallelism. Okay. So when you run a program, a logic on a CPU, it runs sequentially. You know that, right? Is that a known fact? I think I'm making people sleep here. So when you run a C program on a CPU, let's say a single core CPU, how does it run? Sequentially, right? Step after step. FPGAs are completely different than that. There everything is implemented in hardware. Everything runs in parallel instead of sequential. Okay. So for example, if the data that was coming in 61.44 MSPS, whatever data was coming in, but the ADC is only 12-bit. Okay. So it will send a sampled version of a signal 12 bits long, and it will try to give it to CPU. CPU talks only in 16-bit, 32-bit, 64-bit. Have you ever seen a CPU which works on 12 bits? No, right? So somebody has to pitch in to convert that 12 bits to 16 bits. Okay. And it's not just that you are getting the 12 bits from one channel, you are getting it from 4 channels. So somehow you have to buffer the first one, wait for the second channel to come, third channel to come, fourth channel to come. Zero pad everything to make them 16, 16, 16, 16. What's the total size? 16 times 4? 64. Now it can perfectly fit on your CPU bus. Send it to CPU, run your algorithms there, DSP algorithms, and CPU will do its job. Okay. So these are the jobs for the FPGA. Okay. So on this Pluto board, there is an Xilinx FPGA, which is basically Zinc 7000. So it has an FPGA as well as a processor. If it has a processor, so it can run C code also on it. Okay. So I don't need to take out anything out of this. So this is basically a computer with an FPGA on it. So you can run your modem software directly on it. Okay. No need to connect it to PC or anything. So SDL design is responsible for transforming and buffering ADC DAC data suitable for ARM processors bus. I just explained that. Then connect the transceiver to DDR memory via DMA. Okay. Right. And interpolation and decimation filters, that also I spoke about. This is the receive path in the FPGA. So this is where your 12-bit ADC data is coming in. This block is going to zero pad and make it 16-bit. Okay, and wait around and then create two INQ paths. Then this is a decimator. This is an extra decimator if you require so. This will make it 64-bit, and this is the DMA. DMA means direct memory access. Have you heard of this term, DMA? In microprocessors you would have listened, right? It's the task of this guy, because this might be a single core system running at 600 megahertz, might not be able to cope up with the high data rate that is coming in, right? So you are running an operating system on your CPU, so it has to do your tasks also. Okay, the user, when you are typing, who is reading? CPU is reading. When the network packet comes, who is reading? CPU is reading, right? Now you are sending ADC data to it, and you are keeping it at such a high rate key. If it tries serving that, then when will it do your tasks? This is why laptops crash. There is too much happening on one particular task that other tasks are not being able to be scheduled, right? So this is the job of the DMA, to avoid overloading the CPU for data path tasks. So if there is a high stream of data coming in, this guy will directly go and take charge of the memory, DDR memory, and start dumping it without the involvement of the CPU. That is why it is called direct memory access. For that, what you need to do, the CPU, before initiating any of these things, the data will keep coming, hitting a wall and getting dropped. You have to first configure this guy. Okay, man, I have got these many addresses in my DDR memory. You are responsible for it. Whenever any data comes in, you dump it there and give me an interrupt. The data transfer is complete. You understood? So CPU is no longer involved in this picture. CPU can do other tasks. This is what is called multitasking in operating system parlance. And what I showed here, if you do further study on, can you give me 15 minutes more on this? Because I'm at a very critical stage. So in this entire FPGA block diagram that you see, it is difficult to make out, but these two blocks has something called slave axes, means they can be configured and controlled from the CPU, but not this guy nor this guy. Sorry. These two guys have slave axes, not this guy and this guy. Okay, so whoever is axis means AMBA extensible protocol. This is how a processor talks to any peripherals connected to it. Okay, you have heard of SPI, I2C, USB, all these things, right? These are all controllers. They are attached to the CPU core via a bus. Okay, that bus is AMBA bus, some terminology. Okay, and they have a set of protocols called axis protocols. So anybody wants to do anything on the bus, it has to go through the CPU. Okay, so a CPU wants to configure DMA, it needs to have a attachment to this slave axis. So this guy will now be a slave, and particular to that there will be a master axis port here. So a CPU will be the master, and who would be the slave? The DMA controller. So that is how you program the DMA controller to do any data transfer. Okay, likewise this guy also. And these two guys will have addresses on the CPU's memory bus. So when you write a C code, okay, and you want to configure the DMA controller, you have to first have its address with you, right? So DMA controller's address is this one, right? And this is another guy who is responsible for buffering and all that, zero padding and all that. So if these two blocks are on my memory bus, my CPU can control them. You need to write a program so that CPU can control them, right? That program is called a driver. Now that driver could be a bare metal C code, or it could be a driver attached to an operating system. So what is an operating system? It's basically a kernel on top of which there is a user space. When you are talking to a laptop, all you are seeing is a, tell me, come on, user space. You cannot directly talk to the kernel, right? So the kernel is the heart of your operating system. Every operating system has a kernel. Windows has it, Mac has it, Linux has it. Okay, so kernel is the guy who is responsible for dealing with the hardware. So how do you talk to the kernel? So kernel exposes certain APIs. Okay, and those APIs can only be called via system calls. Okay, so when you write a C code, for example, you compile that code into an executable, right? When you are compiling something into an executable, you are bringing in libraries. Can you name one library at least for me? When you write a C code, the very first header file, what do you include? stdio.h. Right? So that stdio.h, what is it basically? It's a declaration of certain functions which you have not written. Who has written? When you do printf, did you write printf yourself? You pulled in from some library, right? So that stdio.h will have a corresponding stdio.c file, or maybe some other name, I don't know. They are part of glibc, which is written by GNU Foundation, which one day decided ki I must provide for the betterment of this world an interface to the kernel. Okay, so when you write a C code, you have to first bring in all these libraries because they are responsible for doing the system calls, and the system calls translate to the kernel. Kernel awakes. Most of the time kernel is sleeping. Okay, when you do a system call, kernel will awake. Oh, kya hua? What do you want me to do? Okay, then you would say ki, okay, go configure the DMA driver. It would ask, where is it? Where is the DMA controller? You will pass on the address to it. This is the address. Okay, fine, I know where the DMA controller lives. I can see it on my bus because it is memory mapped to my bus. I can see it where it is. What do you want me to do? Then you have to give it whatever you want to write to the registers of the DMA controller. This is how you control things. Okay, even if you want to design your own controller IP for whatever reason you have in mind, you will have to provide some registers, memory regions in it, and then map them to the address bus of the CPU. So whenever you write a code, C code, you have to write to those registers, and then you can start glowing LEDs or make something happen on the hardware. This is how embedded systems work. Operating systems make it much more abstracted. Okay, so this is the driver. I cannot talk about, see, I'm on LinkedIn and I have written for past 2 years several articles covering this. So I have one series which is on embedded systems, the other series on embedded Linux, everything. So you may have to read all those things to understand what I'm talking about. What I'm saying is ki when you compile your own Linux to run on your hardware, first of all the kernel needs to know ki what is there on the hardware. Okay, it can't be just one CPU. A CPU, different vendors make different CPUs. You take STM32, it has a different chip. You take some other brand, they will have different chips. So there will be a CPU core around which there will be Ethernet controller, USB controller, SPI, I2C, all sorts of. Some might not have anything, bare metal, just one CPU with basic I2C or SPI around it, right? So different microcontrollers or microprocessors will have different hardware architectures. Now if you try to run Linux on top of them, microprocessors, if you try to run Linux on top of them, you need to make Linux aware ki what is there on the CPU and around it. If you don't make it aware, you just tell it this is a 4-core CPU, that is all information I'm going to give you. What would Linux do? You just saw something happen to my laptop. What was it? I tried to connect HDMI, nothing happened. Why? And I kept murmuring something about it, ki why it is not happening. Did you pay attention? Driver. So driver is the thing that tells the kernel this is how my hardware is laid out on this particular board. I have a CPU, but I also have an Ethernet controller. I also have an HDMI controller. If I don't write a driver or give it a driver for HDMI controller, no matter how many times you try to connect a HDMI code, nothing will happen. Okay, but the moment you connect it, it will raise an interrupt. Kernel will awake. What happened? Some interrupt on this HDMI line came to me. Okay, do I have a driver for it? Yes, the kernel says I have this driver at this location. It will invoke the driver, assign a proper memory maps, and immediately that HDMI controller will take charge of the DMA bus. It will start sending whatever samples are there on my display card memory output. It will start sending to the monitor, external monitor. Okay, that's how things work. So to make aware to Linux ki what hardware is running on my board or system, there is something called device tree binary. It's basically a hierarchy tree, right? So there is a root node and there are many leaf nodes. So the root is your CPU, and leaf nodes are all the other peripheral controllers. Okay, so I just showed you in that FPGA block diagram two devices which were connected as slave axis with their addresses. So they have to be, so the Linux kernel has to be made aware of those things, right? So device tree file you can find here, Linux architecture, ARM, boot, device tree source, and this is the device tree file for this particular board. So if you try to run a Linux kernel on this board, it will look into this guy and find out these two entries there. One is that that guy who was doing zero padding and making 12-bit to 16-bit, and the other guy who was responsible for DMA, so DMA controller's address. Okay, so now Linux is aware of these two hardwares, actual hardwares, and where they are located. Device tree information will only tell you where they are located, address, and what IRQ interrupt lines they are connected to, and certain other properties. How many channel DMA? DMA can be many channels. It could be different modes of DMA, scatter, gather, and all that. So all those things are configured here. Okay. Now Linux knows about it, but just knowing about somebody's existence doesn't help you with anything, right? You have to actual data transfer. You need to have properly written code, which the kernel knows to execute to do anything with that particular device. That's the driver. This is not driver. Okay, so I have written where you can find the drivers for those. So for this guy, the driver is located at Linux drivers DMA axis, this thing. And for this guy, it is located at, this is a funny term, industrial IO. So it is located here. I don't think there will be enough time to cover all this. So Linux driver ecosystem is quite complicated, and so what these people, Linus Torvalds, you might know him, right? So what these guys decided was, okay, for every new device that comes out, I cannot write a new driver and add it to my Linux kernel. My Linux kernel will become bloated. There are thousands and thousands of devices, thousands and thousands of separate drivers for them. No, we need unification. So several frameworks are there. For SPI, for I2C, there are frameworks. Then most of the time we engineers, we like to attach things to our CPU. In this case, we are trying to attach an RF front end via an ADC. So ADC, right? There are hundreds of different types of ADCs, but they all do the same thing. What? Analog to digital conversion. Okay, so if I can write a unified library, that would be saving my day. Okay, so analog devices makes a lot of ADCs, so they came up with a concept called industrial IO. So this is a unified set of kernel functionality called framework, wherein they bring in ADCs, IMUs, DACs, all sorts of sensor data capturing sensors, right? So they brought it under one umbrella, or something called APIs, application programming interface. So you can program them with using just one kind of API. You don't have to learn every time a new device comes out. You don't have to rush through its data sheets and write new code for it. The same set of APIs you can apply to those also. That's called industrial IO system. And for example, if you have a 3-channel ADC, it will appear to you. See, I told you about user space. There is a kernel space. You cannot talk to it. User space is where your programs run. They are translated to kernel via the glibc or those kind of libraries, right? But user space needs to know what all hardware is running. Fine, I don't want to control it. You control it, man. They say to the kernel, but let me see at least what is connected, right? In the user space. So users, if you see, have you worked with Linux? Most of you? Any of you? Ubuntu to dekha hoga. Right, you have run Ubuntu, right? So you know what folders are there. Home, root, all those, etc, dev, all those things, right? Those are basically fictitious. They don't exist on hard disk. They are in the RAM. This is called virtual file system. Okay, so it's how kernel brings up all the device information and puts them in a very systematic way for the users to see okay, what all devices are there on the system, and you can find them in /sys bus IIO devices. So if you're dealing with a 3-channel ADC, it will appear like this. Okay, since it's an ADC is an input device, so the first term here will be in. Okay, now in voltage, then which number index for it, 0, 1 and 2. So had it been an accelerometer, it would be in voltage X, X, Y, Z, 3-channel accelerometer, right? Those kind of things. So if you go and do a cat on this, you'll be able to read the contents of the ADC basically. So from user space, you can actually read what the ADC data was sent to your kernel and made available to you in the user space. Okay, that's what it is saying. So your application runs here, it does a system call to the virtual file system. This is the kernel area which is responsible for handling the hardware requests. Okay, this is where your IIO system runs, basically taking the data via the device driver, storing in some kind of a buffer and making them available via virtual file system. And in this virtual file system call interface, this is where either you have to write the code yourself how to interact with the sysfs, or you can use ADI provided libraries. Okay, so these are your devices. This is the Linux kernel and this is the user land where you install ADI's devices, library, and then whatever application you write, they will talk to the library. Library will be responsible for pulling the data up. Okay, now the beauty with this thing is whatever you see here is just this Pluto device. Okay, this is your hardware, basically the transceiver chip that I showed. From there to DMA to memory, it has been attached to the CPU, and on CPU what is running? OS kernel, right? Once it is available to the kernel, now this library is able to fetch data from that. Okay, so the data, analog data sampled via the chip, send it to the DDR. Now I can read via the kernel in this LAN. Okay, and my application is running on this particular board. But if my board also has network connectivity, the same data I can read on networks also. So basically, if I attach it to a PC and my PC is connected to LAN, I can get this data from any other PC on the LAN. Now just imagine how powerful that concept is. So your modem or SDR or whatever, this device might be deployed in the field. You don't have physical access to go there, but that thing is connected via 4G and all that, basically some networking capability. Now you can access it from anywhere in the world. That's the power of software abstraction. Okay, instead of dealing with the hardware at the hardware level, now you can access it remotely. Okay, that's the beauty of SDRs. I will not talk about this, how to create a Linux, completely running Linux system that can run on this. These are the steps actually. OFDM modem design. Okay. Okay, can anybody tell me what is the full form of OFDM? Half battle is won. Orthogonal frequency division multiplexing. Have you heard of the term QAM? Quadrature amplitude modulation. So quadrature amplitude modulation or QPSK or BPSK, these are all modulation techniques. Okay, this I and Q signaling that I mentioned, you just sample them. Those samples are called quadrature samples. Now how are you going to sample them? You want to collect 2-3 samples together and then call it a symbol, or you just take one sample and call it a day. Okay, this sample is one symbol, this sample is one symbol. Okay, symbol is not the same as sample. These are two different things. So if you take a BPSK, right, so it will have either +1 or -1. Okay, just two samples of that signal and you make it one symbol. To distinguish between the levels of BPSK, how many bits of information is needed? Whether to say that something is 1 or -1, how many bits I need? Only one. If I give you 1, then you will say it is 1. If I give you 0, you say it is -1, right? For QPSK, 2, right? For 16 QAM, 4. For 64, 8. You know the drill, right? So what it means is, for BPSK, I only need 1 bit of information to tell whether it is 1 or -1. For QPSK, I need how many bits? 2 bits. So you wait for one sample, then second sample, you make it as one complex number, right? Because in QPSK, you know the constellation diagrams, right? So it will be in, each of the quadrants, QPSK, right? So that complex number will tell you which combination of 2 bits you just transmitted. Okay, if you transmit this particular complex number, it was this combination of 2 bits, 1 1. If you transmit this one, it was this combination 0 1, like that. Okay, that's called symbol. So what happens is you have stored your data as these complex numbers in memory, RAM. Now you want to transmit them. How do you transmit? So you take that serial data one by one. Okay, now all that data might be belonging to a single user, or it might be coming from many users. So when you have a home router, all your family members are accessing it. Okay, they have separate streams. You are watching YouTube, somebody is watching Netflix, somebody is doing WhatsApp or something. They're all sending their packets. Okay, they will all come into a buffer. That buffer will be converted to a serial stream and be sent here. Okay, the first constellation point might belong to you, somebody else's constellation point might be coming next, like that. A train, a stream of samples, right? You collect them in a buffer. You take an IFFT. What does IFFT do? Inverse Fourier transform. So Fourier transform, you know, right? Converts time domain to frequency. So inverse Fourier transform would be doing the opposite, right? So what you do, you take those complex numbers, okay, serial to parallel complex numbers, and you use them as coefficients to weight your carrier frequencies. So you know Fourier series, right? There are coefficients which are weighting the basis functions. You know the basis functions, right? E raised to j 0 omega t, e raised to j 1 omega t, e raised to j 2 omega t. These are your basis functions. Now you can choose the first basis function I will weight by some complex number. The second basis function I'll weight by some other complex numbers, right? And then I'll add them together. What do you get out of it? A time domain signal, right? Which would not look like sine or anything, because it's now a combination of all the frequencies of different weights. Okay, that is what will appear here. Okay, you transmit that. There is some concept of cyclic prefix. Basically, it is used in OFDM to mitigate multipath fading effects. Basically, at the receive end, here again you convert that parallel to serial, give it to a digital to analog converter, and transmit over the air. On the receive side, you receive it. You do a filtering again, remove the cyclic prefix because this doesn't add any value. This was only done to remove the fading effects. Then to cancel out the effect of IFFT, you do a FFT. Okay, this equalizer is to mitigate the channel effects basically, because when I transmit from here to there, depending on what is there in between, different frequencies will be treated differently, right? Some frequencies will be diminished, some would be let through easily, right? So when the signal reaches to your end, it would still be a combination of different frequencies because that's what you transmitted, right? But some of them arrived perfectly fine, the others were attenuated. So your end result would be a different signal completely, right? Isn't it? So what if you knew what the channel response is? You can correct for it. It's called equalization on the receive side. Okay, so you do that here, and then again slice in parallel to serial. So here at this point you can separate out the stream, which one belongs to Netflix, which one belongs to YouTube, and all that. Okay, this is just OFDM, and beyond this there will be QPSK or whatever modulation scheme you want to put. An OFDM transmitter would look like this. This same structure is used everywhere, whether you use WLAN, Wi-Fi, or you use 4G LTE, 5G. Wherever you go, OFDM is standard. This is what it looks like. Okay, so there will be a synchronization sequence, there will be a reference signal. Synchronization signal is what is used to find where your frame starts, because over the air transmission, right? So you are standing here with your ears open, but can you hear anything? Not unless somebody is saying something, right? So but you have to be open all the time if you want to catch what they are saying, right? So when somebody transmits something, how do you know when it starts? So for that you have to be listening for a very particular kind of sequence that is called synchronization sequence, that will tell you where the frame starts. Okay, then the reference signal, which is what I mentioned about channel equalization. Okay, so you send a very standard reference signal which is known on the receive side, but you know when you have received this reference signal on the receive side, it would have gone through the channel and attenuated in different ways, है ना? But you knew what signal was actually transmitted. From there, now you can reverse engineer and find how the channel is behaving. Now you can correct for the channel via equalization. That is the use of sending this guy. Then you have to send a header. Okay, header means, now I talked about QPSK or BPSK or whatever, right? When do you choose what modulation scheme to? I won't be able to show demo because there is no time, but I want to leave you with a proper knowledge of it. Okay, if you want to go out of this room and implement your own SDR, these are the things you should know. I hope I have made something clear to you. Okay, so what is a header? What is the use of a header? See, when my environment is very noisy, okay, should I pack more number of bits and send one sample like that? What if there are more errors? A lot of bits would be destroyed, right? It would be much more difficult for you to decode a 16-bit symbol. It's much easier for you to decode a 1-bit symbol, isn't it? So you can easily detect a BPSK. There are only 2 levels. You just have to do a threshold detection, whether it is 1 or -1, right? But if I tell you it's a 64 comm signal with all small constellation points, if one goes in error, the chances of it being confused with any other nearby bits is much higher than for a BPSK, right? So that is why when you do satellite communications, you do not more than BPSK, okay, or QPSK max. But in Wi-Fi, you can go up to 256 comm. Why? Because Wi-Fi is across the room only, right? The channel effects are not that strong, so you can transfer at much higher data rates. That is why if you want to make a call via satellite, not gonna happen. But if you want to make a call via WhatsApp on Wi-Fi, sure, why not? It can support all that. You can watch 4K HD videos you can watch on Wi-Fi, right? It's because of this reason. So if your channel conditions are allowing you for wide bandwidth transmission, you bump up your MCS, modulation coding scheme. If they are not, because Shannon says their SNR is low, bhai, I cannot transmit now that much at that channel capacity. Your channel capacity itself is low. And channel capacity is related to bandwidth. If your capacity is low, your bandwidth has gone down. You cannot transmit at 400 megahertz bandwidth now. You understood now the concept, right? So when your channel conditions are unfavorable, you drop down your modulation and coding scheme. So instead of 64 comm, you come down to just BPSK. Okay. This is called adaptive modulation and coding scheme. Okay. This is where the play of AI and machine learning comes. Okay. This header is a key guy. Once you know something has arrived, once you know what the channel conditions are, now the header has to be the guy which tells you what follows me is modulated in particular way. Okay, you might choose to send 64 QPSK here, 64 comm here. Okay, but how would the receiver know at what modulation scheme did he transmit? I am not aware of it. So that information is contained here. So header will tell you what follows in the payload is modulated at 64 comm. You better be ready for it. Okay. But first of all, the header should go through, right? If the channel conditions are, that is why it uses BPSK, because it is easier to transmit it in a noisy environment. Okay. This interleaving, some other concept basically to spread out the noise, the error vectors basically, because when noise occurs, right, it occurs in bursts. Have you noticed that when somebody is talking like me on the stage, suddenly my phone will start doing some SMS thing and you will hear it out, right? Pop, 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 like that. That is bursty noise, right? It happens for certain duration and it will induce errors in your bit stream. And rest of the bit stream is fine. Okay. But when you work with convolutional error correction codes, they are dependent on the locality of the relations between bits, right? If these bits are all messed up, how can I extract any information out of it? But if these errors I can spread out over the entire thing, I am maintaining my locality piecewise. Okay, so my convolutional error correction codes will work much better if I somehow can interleave the bit errors, so that this bursty thing that is happening should be spread out, so that my encoders would have a higher chance to decode that signal. That is why interleaving is used. And CRC is basically cyclic redundancy check. So once header goes through, then comes your payload. Okay, this pilot insertion, I'll tell you, when you are sending your payload, you are inserting some pilots also, because despite the channel being absolutely good, there is something called local oscillator running on my device, right? And for such cheap devices, the LOs are not very good quality, not very precise. Okay, they can drift here and there. Okay, so when they drift and your signal duration itself is quite long, and these guys are drifting, this will affect what is called as the orthogonality of all the subcarriers that you are trying to say. Basically, destroying your IFFT, whatever signal you created, right? So when you do an FFT, you will not be able to reverse the effect of FFT. You understood? So I'm just explaining all these things. Okay. So payload there. Then you store everything into RAM. Then you do your OFDM, whatever I mentioned in the previous slide, interpolation filters, and send it across. Then you have to reverse all these things on the receive side. Okay, I don't want to go into all that. This information you can find on OFDM pages on MATLAB's wiki. Okay, there are several examples of that, but I basically gave you a crux of it. You have to first decode the header. Those are the steps for it, and then you have to decode the payload modem implementation. I am not going to show all this. So this is the code which is running here actually. I needed Ubuntu. See, should I show the demo, or should I explain it quickly in 5 minutes? What was the demo about? I think I'll explain. So I have two Plutos, this one and this one, okay? And I have antennas also, and they are both tuned to work at 915 megahertz, right? So as long as whatever I have explained, there is an RF front end, there is an transceiver chip, there is an ADC built in, and that ADC sends data to the FPGA. From FPGA it goes to the Linux OS kernel. From there it is made available to the user space. User space is where this OFDM, whatever I mentioned, flowchart, this is implemented in C. Okay. So this is running one modem, this is running one modem, full duplex, kind of. So there is one guy here who can transmit and receive, one guy here who can transmit and receive. How is it different than any other thing? No MATLAB, no nothing, everything built out of open source. Okay, so you can do this at your own place. Only you need to buy these two things. Everything is free and open source. Okay, now I have tried with, I got up to 272 kbps, 64 subcarrier wala OFDM, and I was able to do 16 QAM on this, because 915 megahertz is not the really sweet spot for this guy. The antennas are too tiny, they work very good at 2.4 and 5 gigahertz, but not lower frequency. So I had to attach a bigger antenna. I have not tested it out yet. So basically I'll power this on, and to see the messages receiving I have to connect it to my laptop. Unfortunately it's not happening. I should have tested. At home it was working. Here somehow I'm not able to connect the HDMI. So sorry for you guys. So I can show you if you stick around. So what happens is, this will come up. It will start listening for a neighboring node. The moment you power it on, this will also start sending data. Okay. What are they sending? So they are sending what is called as, they would send a 52 byte of message, basically empty message, but it is just telling ki I am alive. This is my address. Okay, what kind of address? Ethernet address. Okay, so what is happening is, all that things I have shown you, the RF part, digitization part, and everything, that's called physical layer. Okay, on top of that, what comes? Do you know OSI stack? What is about physical layer? Louder. Data link layer. That is where your Ethernet works. When you connect an Ethernet cable, that is where it is working, right? So Ethernet works on Ethernet frames. Okay, point to point links. Okay, so once it starts sending OFDM packets and everything, this guy decodes it. Okay, decodes it means from there it will extract the bit stream, ASCII values, and it will understand, oh, this is what it sent. It sent its Ethernet address. So it will add that Ethernet address to its routing table. Then this guy will start sending. It will start sending its own Ethernet address. This guy will know about it. Okay, so they will both maintain their routing tables. Ki I am connected to that guy, and that guy will know I am connected to this guy. Okay, will it work only on 2 devices? Absolutely not. I can bring one more Pluto, 10 more Plutos, 400, 500 more Plutos. The moment I switch them on, they will all start talking to each other, and they will start sending point to point data to each other. right? And there is something called Batman. Its full form is Better Approach to Mobile Ad Hoc Networks. Okay, so what you would have created here is a mesh network of nodes which are talking to each other via OFDM. Okay, so each one of them is creating a Wi-Fi link, not connecting via Wi-Fi routers here, anything. So they have their own Wi-Fi mesh working at 914 megahertz, 20 megahertz of bandwidth. Okay, they can all talk to each other, maintain their routing tables. Why routing tables? Because now if I connect this guy to my laptop, this guy is connected to another Pluto and 10 different Plutos. Now I can reach any of those Plutos from my laptop because they have set up a link. Okay, this is the demo that I wanted to show you, and it's all completely built in open source software. Okay, hope you have understood how communication happens. What is the hardware infrastructure? What is the software infrastructure? For more details, it will take you minimum 3 to 4 months to build it yourself, test it out. Everything is there on my LinkedIn thing. You can come across, connect with me and try your hands on. Okay. From academics, professors, I would request you to make sure that you buy these for the department. Okay, these are very handy tools. I have been working on them for last 4 years. I have built modems, I have built radars with them actually. I also had a video, unfortunately I won't be, it's on my WhatsApp. I have made a monopulse tracker with this actually. So it's a, this is old one. This new ones have 2T and 2R, 2 transmit and 2 receive. All you need is 2 receive channels. So one channel, so if you know the principle of monopulse tracking? In radar you would know, right? What is it? Yeah, sum and difference channels basically. So you get 2 channels, two analog signals are coming in, you digitize them, you create a sum channel, you create an difference channel. From there you can find out which direction is your target. Okay, but how do you know which direction is your target? So these are 2 receive antennas. Okay, if the target is in the bore site, the signal coming in will impinge on these 2 antennas exactly at the same time. So phase difference will be 0. But if the target moves like this, target or emitter moves in this direction, the signal arriving at this antenna would be faster than the signal that arrives here, right? This will face some delay. That delay makes phase difference. So if you sample these signals, you can be sure that there will be a phase difference between these two. But I have already showed you how to find that phase difference, right? So you can use that phase difference to figure out which direction is your target, this direction or this direction, because phase Rx1 will have a different phase than Rx2 if the target is here, and when you move the target to this side, then the phase difference changes, right? So you can actually lock on where the target is moving basically. Yeah, so with that I will stop today. USB, and that's the beauty of Linux. It implements something called RNDIS, and the way to pronounce is horrendous. So basically Ethernet over USB. Okay, some modern implementation. This is free and open source. Everything is free. Yeah, in fact the PCB layout is also free. You can copy that, modify it and build your own SDR also. Okay, which is what I'm going to do next actually. I want to actually not rely on the USB Ethernet. I want to actually put a proper USB port there and replace the chip, because this Zinc 7010 is a very limited FPGA. Whatever SDL is running on it, you have to live with that. You cannot add custom logic. If you want to build this modem entirely on FPGA, this chip will not allow you. You will have to scale up, maybe buy a Z board or something which has 7020. But both these chips are pin compatible. So I'm actually planning to replicate this design, remove this FPGA, put that one. And this has this transceiver chip I showed, AD9361. That's a very expensive one. Like it costs you around 50-60,000 rupees. This one costs you 19,000 rupees. But the problem is this is a binned version of 9361. Basically, they in the tape out process, whatever happens, right? Some chips do not function well. They test it out. They see, okay, RX1, TX1 is working fine, na? Isko kam daam pe bech do. Right? So that is what comes in this actually 9363. So 9361 2T 2R pakka it will work. So you can use MIMO also. That is what I mentioned here actually. My next project is to implement MIMO modems using a slightly scaled version of this hardware and adaptive MCS. I didn't talk about machine learning, sorry about that, but you would have got an idea. That header that I was sending, in that there was this reference signal I was sending. That reference signal is your means to know what's happening to the channel in this room. Is there interference? What kind of frequency selective interference? So which machine learning algorithm should I use to reverse the effects of it? That's a completely new domain in itself. And MIMO is all about that. So when you hear about massive MIMO and the research that goes in 5G and 6G is all about that. This is where it starts. Okay. That is all for today.
Thank you, sir, for such an inspiring talk. We also extend our gratitude to Nalesh, sir, for chairing this session. Before we conclude this session, we now invite Dr. Neeraj Kumar to kindly accept a token of appreciation as a small gesture of our thanks. I request Nalesh, sir, to do the honor.
So with that, we conclude the last talk of the session. As we come to the end of day 2 of APSYM 2024, we would like to extend our heartfelt gratitude to all the speakers, chairs and participants who made this day a grand success. We hope these sessions have enriched your understanding and sparked new ideas. Let's carry this energy forward to the next day as we continue our journey of learning and innovation.